we're going to use mathematical induction to prove a formula 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 and so on. So we want to add the integers from 1, 2, 3 all the way to a certain number. But we're not going to write down all those numbers we have because we may have to add the first 50 numbers. We don't want to write down all the 50 numbers. So we're going to use 3 dots to represent the numbers we omitted. We're only going to write down the last number. And the last number we don't know either. And we're going to use a variable to denote it, letter n. And where n here is going to be an integer greater than or equal to 1. And so what is n? N actually could be just 1. So if n equals 1, we're not going to have 2, 3, 4, anything. We're just going to have one number. Because this what we call the sum of the numbers here actually means we are adding the numbers from 1 to n. So add numbers from 1 to n. So if n equals 1, that means pretty much means we add numbers from 1 to 1, the integers from 1 to 1, which is just one number. But n could be 2. If n is 2, then we're adding numbers from 1 to 2. Or if n is 3, then we add integers from 1 to 3, which is 1 plus 2 plus 3, and so on. So if n is 10, then we're adding integers from 1 to 10. So that would be 1 plus 2 plus 3 plus 4, 5, 6, 7, 8, 9, 10. Okay, that's the left-hand side. So how many numbers do we have on the left-hand side? Depends on what n is. And the right-hand side is just one term. We don't have it's a change in number of terms. We only have a fixed function, n times n plus 1 over 2. So this is a formula we're using a lot of math classes, especially in calculus class. So we're going to try to prove this. And theoretically, we need to prove this formula holds for infinite many integers. So if n equals 1, we need to show the left-hand side equals the right-hand side. If n equals 2, we get a different formula. We need to show the left-hand side 1 plus 2 equals the right-hand side, replace n with 2. If n is 3, we need to show 1 plus 2 plus 3 equals 3 times 3 plus 1 over 2. If n equals 4, and we are adding numbers from 1 to 4, which is 1 plus 2 plus 3 plus 4. And so I'm going to write down what if n equals 4? What do we get? And we get 1 plus 2. We're adding numbers from 1 to 4 and equals the right-hand side, replace n with 4. So I'm just writing down one of them, but technically we need to write down all the formulas. N equals 1, n equals 2, n equals 3, and continue n equals 5, n equals 6, and so on. But we know there are infinite many integers, so it's not going to be possible for us to prove every single one of them. So what we're going to do is we're going to use mathematical induction. We're only going to do it by 2 steps. Step 1, which is called the basis step. In this step, we're going to prove the formula holds for the lowest integer given. So if they tell you n is greater than or equal to 1, and the lowest integer will be 1. But sometimes they may tell you n is greater than or equal to 3, or n is greater than or equal to 0. So it depends on what they tell you. So in this step, we're going to prove, so n equals 1. And what's the left-hand side? It's going to be adding numbers from 1 to 1. So left-hand side, it has only one number, just 1. On the right-hand side, we replace the letter n with 1 and reduce this. So we get 1 times 2 over 2, which is 1. And we can see the left-hand side equals the right-hand side. So the formula holds if n equals 1. Now, next step, we're not going to prove the formula holds for n equal to 2 or n equal to 3, and we're going to prove a general case. We're going to assume the formula holds. So this is an important step right here. We're going to assume the formula holds for n equal to k, integer k. By the way, all that part in the corner here is just something we work on the scratch paper to help us understand the problem. You don't have to write all that in the proof. Okay, so the one we're going to assume right here the formula holds for n equal to k, and our goal is to prove, we want to prove the formula holds for n equal to k plus 1. So why do we do that? So the assuming part is the hypothesis, which we talked about before. So this is like, in this step 2 is like proving if this formula given holds for n equal to k, then the same formula holds for n equal to k plus 1. Because k is a variable, so this k can change. If k is equal to 1, and k plus 1 will be equal to 2. So let's write down a few cases. Again, this is just the thinking process here. So if we can prove the formula, so k and the k plus 1, if we can prove the formula, if the formula is true, holds for k, which is 1, and then the formula holds for 2, which we have already, is the formula true for n equal to 1? Yes, we already proved it in the basis step. Since we already proved the formula holds for 1 by using step 2, the inductive step, if the formula holds for 1, then formula holds for 2. And we can keep using the inductive step. And since the formula holds for 2, and go back to use the inductive step again, which says if the formula holds for 2, then the formula holds for 3, because we know if the formula holds for k, then it holds for k plus 1. So k to k plus 1, that can be 1 to 2, 2 to 3, or 3 to 4, or 4 to 5. So this can be applied infinite many times, so we can keep doing this. That pretty much proves every single case. So what we do is we proved the formula holds for 1 in step 1. This is step 1. And in step 2, we proved if it holds for 1, then it holds for 2. Then by using step 2, then we got the formula is true for 2. And then we go back to use step 2 again. Because it holds for 2, then we can say it holds for 3. And use step 2 again. If it holds for 3, then it holds for 4. And use step 2 again, it holds for 4, then it holds for 5, and so on. So that means the formula holds for any n. 1, 2, 3, 4, 5, 6, if we keep going this. Okay, so this is the idea. But the important step is the step 2 right here, which we haven't proved. So how do you know if the formula holds for k, then the formula will also hold for k plus 1? So that's what we need to prove. Okay, so if we can prove that, and by what the explanation here, we know if we can prove both cases, and then we proved, the formula holds for every single integer, every single positive integer n. So let's see if we want to prove. So this is what we know. The formula holds for n equal to k. So let's write down the formula. What is the formula if n equals k? The left-hand side is adding the integers from 1 to n. Since n is k, so which is like saying we're adding the integers from 1 to k. So that's going to be adding 1 plus 2 plus 3 plus ... plus k. And the right-hand side, is going to be replace n with letter k. K times k plus 1 over 2, because n equals k right here. Okay, so this is the formula. We assume this is true. And then we want to prove the formula holds for n equal to k plus 1. So we need to write down the formula. What is it what is the formula if n equals k plus 1? So again, this time n is going to be k plus 1. So the left-hand side is going to add the integers from 1 to k plus 1. So that's going to be 1 plus 2 from 1 to all the way to the last one, which is k plus 1. The last integer we're going to add. And we're also going to write down the integer right before k plus 1, because they're consecutive integers, so which is going to be k. And we omitted a bunch here. Now on the right hand side, we're going to plug k plus 1, because this time, this formula n equals k plus 1, so I'm going to replace n with k plus 1. We'll put k plus 1 times k plus 1, which is k plus 2. Because we replace this n with k plus 1 and plus another 1, which is k plus 2. So this is the formula we want to prove. And how do we prove this formula? So this is the hypothesis right here. We start with this hypothesis. We want to prove this one. So we know this is true, and we don't know if this is true. Okay, but we can make connections between what we know and what we don't know. So first, compare the left-hand sides. We have the left-hand sides, we have numbers we're adding from 1 all the way to k. And the same thing here, we're adding 1 all the way to k, but with the extra integer k plus 1. So in order to obtain the left-hand side, we're going to add k plus 1 to both sides. K plus 1 to both sides. So the left-hand side, we started with 1 plus 2. We started with 1 plus 2 plus 3 plus k equals k times k plus 1. So I pretty much copied the original assumption again. And we're going to add k plus 1 to both sides. So the black color is the one we're going to add to both sides. If we add that, you can see the left-hand side is exactly matches the left-hand side of the formula we want to prove right here. But the right-hand side is a little different, so we want to get exactly the same thing. So we're going to use some algebra to prove that, and we know that this is, since the first one is a fraction, so we're going to make the second one also a fraction, put a 1 underneath, and then we can equal the denominator by multiplying 2, both top and bottom. So now we're going to get a common denominator 2, and we're going to add the numerators. So that when we add a numerator, you don't really have to add them, multiply out, and combine like terms. Make sure you, because this is what we want to get. We already got the bottom too. How do we get the top? So this is what we do. We can see they have a common factor k plus 1. So we're going to factor out the common factor k plus 1, k plus 1. That will leave us k plus 2. And that's exactly what we need. So this is what we did. We start with the formula for n equal to k, which is right here. And then we added k plus 1 to both sides, and the left side will become the sum of from 1 all the way to k plus 1s. But the right hand side, after we use some algebra skills, we got k plus 1 times k plus 2 over 2. So we proved this is going to be true. At the beginning, we didn't know if this is true. Now we proved it is true. So we proved if this formula, if I call this formula 1 and this is formula 2, if formula 1 is true, then formula 1 and 2 is true. So that's like we proved. If the formula holds for n equal to k, then the formula holds for n equal to k plus 1. So the important step is the inductive step. And so when we do the homework, they want you to write down step 1, which is easy, write down left and right. They also want you to write down the formula for n equal to k, which is the first formula. And they write down the formula for n equal to k plus 1, which is the second formula. And they also ask you, how do you prove the second one from the first one? So you can just say something like, we can add k plus 1 to both sides.